All right, so in this video, we are going to be deriving the D5d character table, and we're going to do that from scratch. And the way that we have to start out is just the same way we do with any point group. We have to identify all the operations, symmetry operations in this point group, and then group them into classes. And it's useful to think about, the example molecule here is staggered ferrocene, showing this top view here where you can see the carbons of this cyclopentadienyl are offset. And in fact, this carbon lies in between the carbon-carbon bond of the below cyclopentadiene ligand. So this has D5d symmetry. And of course, we're always going to have the identity element. We're using hat notation here to represent that this is a symmetry operation. So every point group has the identity operation, which is the do nothing operation. Of course, we're a D5d point group, so that 5 tells us we're going to have a C5. That's going to be our principal rotation axis. That's going to be a 72-degree rotation. And indeed we are. That's going to take, for example, this hydrogen, put it in that hydrogen, this hydrogen, put in that hydrogen, and interchange all the hydrogen and carbons around this pentagon. So we're going to have the C5 operation, but we're also going to have the C5 two times, right? We can do a C5 twice, and we can do the C5 three times, and the C5 four times. C5 five times gets us back to a 360-degree rotation, which is identity. So that doesn't do anything. And so these are four more operations that we have. We can go ahead and group these 5 operations we've derived into classes. We're going to have the E class. I'll drop the identity class, drop the hat notation here. Identity always forms a class by itself. And then we're going to have, let me just do this in red here to denote classes. And then we're going to have the C5 and the C5-4. Those are going to go together in one class. And the reason why those go together in one class is because you could think about doing a 72 degrees rotation and taking this hydrogen and that hydrogen, or you could think about doing 4 72-degree rotations, and that would take this hydrogen, spin it all the way around to this hydrogen. Well, that's equivalent to just doing a clockwise rotation, rotation in the other direction just once. So the C5 and the C5-4, depending upon how you define your directions, technically speaking, it's your axis systems that you're using, are equivalent. And so that's why they belong in the same class. And then these C5-2 and C5-3 are also going to fall into their own class. So we'll call that the C5-2 class for exactly analogous reasoning. If you think about rotating this 144 degrees, that would be a C5 twice, right? Or you could do this 3 times, right? That would be C5 3 times. But if we do a C5 2 times in the opposite direction, we did the same as a C5 3 times. So again, these are equivalent depending upon how you define whether or not you're doing clockwise or a counterclockwise rotation. So that's why you put the C5-2 and the C5-3 in the same class. Moving along, you can also have the improper rotation axes. And so these molecules have, these D5d molecules have an S10 operation. An S10 operation, that's going to be a 36-degree rotation, right? 360 degrees over n. And so that's going to be an S10. Let's just find that. Remember, your improper rotation is you do a proper rotation followed by a sigma h. So what that's going to do is going to do a 36-degree rotation. We're going to put this hydrogen into here, not go all the way 72 degrees to the other pentagon. And then you're going to do reflection through a horizontal mirror plane, right? And that mirror plane is cutting through the central iron atom there of ferrocene. And so what that does is take stuff from the top and bring it to the bottom and vice versa. So we took this atom, moved it here with the 36-degree rotation, and then we mirror plane it down to the bottom. So you can see how for all these cases, for something like this one, this atom, if we trace that through, uh, let's use a different color. It would go in between here, right? Not all the way over there. And then it would flip up with the sigma H to here. So it traces into a different hydrogen atom, but because it doesn't go into empty space when we do this S2, it is in S10, it is indeed a symmetry operation. So we have an S10, and just like how we can do the C5 multiple times, we can think about what happens if we do the S10 multiple times. Well, if we do an S10 twice, that's going to be a C10 twice followed by sigma H twice. Well, sigma H twice is flipping bottom to top and then top to bottom. That's the same as identity, so that does nothing. So this term goes away, and we're left with just a C10 twice. Well, C10 twice is a C5. And we already have C5. So S10 twice is just a redundant way of writing C5, so that didn't generate a new operation. But we can do S10 three times. That's going to be equal to a C10 three times, followed by sigma H three times, which is just equal to sigma H, because we do three flips is just equal to one flip, right? Top to bottom, bottom to top, top to bottom. So the net was just top to bottom. That's equal to flip. So this is actually a unique operation. So we'd be doing something like taking this hydrogen atom, for example, going 36 degrees in between the two hydrogens, another 36 degrees, and then another 36 degrees going here, and then flipping down with the sigma H going to there. So indeed, we do have that as a symmetry operation. We don't even have to visualize that. We know that just because we proved that we have an S10, because S10 3, we can do it three times, that's going to be a unique operation that we have. Then we can do an S10 four times, and basically the even ones are not going to get you something unique, because that's going to be equal to a C5 two times, okay? Because the sigma H four times, let me just write that out more clearly so I don't go too fast for you guys. So S10 four times is a C10 four times, followed by sigma H four times. We have an even number of flips, so that doesn't do anything. That is just equal to identity. And then that equals to C10 four times, which is just equal to C5 twice. So we already have that. That's not unique. What about an S10 five times? That's an odd one. Odd number of times. So that's equal to C10 five times, followed by sigma H five times. Well, sigma H five times is equal to just a sigma H. So we can simplify that. It's odd number of flips. And a C10 five times is equal to a C2, right? 180-degree rotation. And so this 36 times 5 is 180. We have a C2 times a sigma H. And anytime you see this, a C2 times a sigma H is actually the same thing as an inversion operation. And I have another video where I prove that that is the case, but you can also just walk through this and see that this molecule must have inversion. A very quick example, remember that inversion takes xy, any xyz, any arbitrary coordinate xyz, and takes it to the negative x, negative y, negative z. So a qualitative way of explaining what inversion does is it takes something from that's at the top and puts it at the bottom, takes something that's at the front, puts it in the back, and it takes something that's to the right and puts it to the left, right? So you can see that this one, it's a little bit to the right, it's definitely in the back, and it's on the top of the molecule. And then if you invert it, it's going to go to the opposite of that, a little bit to the left, not the right anymore. It's on the bottom of the molecule and definitely in the front. So this holds. So inversion, that's a unique operation that we've generated here. We can carry on and go S10 6. We have an even number here, so we know that's not going to give anything unique. That's going to be a C10 6 followed by sigma H 6 times. Doesn't do anything. That equals a C10 6 times, which is equal to C5 3 times. We have that here. Go on to S10 7 times. That's equal to C10 7 times, followed by sigma H 7 times. Odd number flips gives us a sigma H. And a C10 7 times is actually a unique operation here. So that's going to be totally unique. So we're going to write that down. It's another operation that we have. And then we have S10 8 times that we can consider. That's going to be C10 8 times. We have an even number of flips with our mirror planes. That equals identity. So that goes away. C10 8 times. And that's going to be equal to C5 4 times. We have that one. And S10 9 times is going to be equal to a C10 9 times followed by sigma H 9 times. Odd number of flips just equals a sigma H. And this is going to be a unique symmetry operation. S10 9 times. If we do a S10 10 times, well, now you're going to get a C10 10 times. Well, C10 10 times is equal to identity. We also have the sigma H 10 times, even number of flips also equal to identity. So the whole thing is equal to identity. We have identity, so that's not unique. So we're done. We've looped around. If we do a S10 11 times, we're going to be back to just identity times S10. So S10 11 times is just equal to S10. So now we've generated here, they're a little bit of a laborious process, but we've generated without much thinking 5 new symmetry operations. We have to group them into classes. Identity is always in a class by itself. So we'll drop the hat notation, put that in a class by itself. And then what we're going to do is we're going to group the S10 and the S10 9. We're going to call that the 2S10 class because there's 2 operations and they're both S10s and they're both S10. And the reason why is because one of these is just the clockwise version of S10, and one of these is the counterclockwise version of S10, depending on how you define clockwise and anti-clockwise based on your axis systems. Just in the same way that C5 and C4, kind of clockwise and anti-clockwise 72-degree rotations, S10 and S10-9 are 36-degree rotations followed by a mirror plane, sigma H, in the clockwise and anti-clockwise directions. And then same thing with grouping S10 3 times and S10 7 times. Those are going to be the same class. We're going to call that the S10 3 class. Okay. And these are going to be doing 36-degree rotations 3 times and then do a flip. And that's either going to be in the clockwise or the counterclockwise rotation. You can think about that as here I do a 36-degree rotation once, twice, 3 times, I got there. Or I do a counterclockwise rotation once, twice, thrice, quatrice, quintice, 6 times, and 7 times. Okay, got to the same spot both ways. And then, of course, in both cases, we flip down to this hydrogen. But those are equivalent. Okay, and then the only other things we're missing here are the symmetry operations that have to do with what makes this a D point group. And so we're going to have to erase a little bit here so I can show you this. But remember that any D point group has n perpendicular C2s. So this case, with a D5 or D5 point group, D5d, but for now it doesn't matter, we're a D5 point group. And so because we're a D5 point group, n equals 5. And so because n equals 5, we're going to have, we know right away that we're going to have 5 and only 5 perpendicular C2s, 180-degree symmetry elements that are perpendicular to the principal rotation axis, or C5. Okay, and indeed there they are. Okay, and they're all perpendicular to the C2. Okay, For visualization purposes later, when we're deriving the character table, we'll only really need to visualize one of these or one of these, maybe some cases two of these at a time. But you can see where they end up. And then there's also going to be these, and that was unfortunate placement here. I'm just going to pause this for a second and move that over. Okay, so I removed this over, and what you can see is that these are the dihedral mirror planes. We know that they are going to be coincident with the principal rotation axis. That means they contain the principal rotation axis. Why? Because they're sigma d. Sigma d's and sigma v's both do that, as opposed to sigma h's, which this point group doesn't have. We're invoking sigma h's when we're talking about improper rotation axis, the s. But it doesn't have a sigma h, but it has these 5 sigma d's. And you can see these, they're d's and not v's because they bisect the C2s. Okay, so they bisect them and actually go through the hydrogen atoms. Okay, whereas the C2s don't. Okay, so it's sort of 45 degrees off from the C2s. And so those are our 5 sigma d's. And so we have to, if we put all this together, put all this together, we got to include our 5C2 classes. It's a 5C2 class. It contains all these C2s. We could call the operations, you know, C2 prime, C2 double prime, C2 triple prime, C2 quadruple prime, C2 quintuple prime. Doesn't really help us. Just call them 5C2s. That's a class. And then we're also going to have our 5 sigma d's. And so in total, if we look here, we have 1, 2, 4, 6, 8, 10, 15, 20 symmetry operations grouped in 8 different classes. And so that's actually it for us. We've done the first major step, which is figure out all the symmetry operations, in this case 20 of them, and group them into their respective classes. And we did this just by thinking about which symmetry operations are similar. So I skipped that step for the C2s and the sigma d's. I think you can see quite easily that all those C2s are very similar, and all those sigma d's, they're the only mirror planes in the molecule, are very similar. So they should go in the same class. So that's the first step, deriving the D5d character table. Now that we have this, in the next video, we can start deriving all the irreducible representations and doing really the meat of the derivation.